Hello and welcome to the Maths 2 component of the online BSc program on data science. Today's video is about linear dependence. So we have seen in the previous video what is a vector space, and in this video we are going to study the notion of linear dependence of vectors. So first of all, let's recall what is vector addition. So vector addition is a binary operation, plus from v cross v to v. So what that means is we take two vectors v and w, and we can talk about the vector v plus w. Okay, so in Rn we know that addition is defined coordinate wise. So x1 x2 xn plus y1 y2 yn is x1 plus y1, x2 plus y2, and so on up till xn plus yn. Okay, so just as an example, if you have 1.5 comma minus 3.3 comma 7.2 comma half comma 1 plus minus 4 comma 5.8 comma 10 comma 5 halves comma minus 3.4, we have to add them coordinate wise. So the first coordinate will be 1.5 minus 4, that gives me minus 2.5. The second coordinate will be minus 3.3 plus 5.8, that gives me 2.5, and I'll leave you to check the rest. Okay. We also have something called scalar multiplication in vector spaces, which means it's a function from r cross v to v. So what that means is you take a scalar or a real number c and a vector v, and then we can associate to that a new vector c dot v, and so remember this dot is corresponding to scalar multiplication. Okay. And it is standard to drop this dot, which is what we did in our previous video. So we are going to just use c times v, cv, okay, and not c dot v. Okay, and in Rn scalar multiplication is coordinate wise again. So c times x1 x2 xn is c times x1, c times x2, c times xn. So here's an example. If you do 0.5 times the vector 1.5 comma minus 3.3 comma 7.2 comma half comma 1, that gives me 0.75 comma minus 1.65 comma 3.6 comma 1/4 comma 0.5. Okay, fine. So let's now look at what is a linear combination of vectors. So this is the key this is the key definition which is going to drive this video and several subsequent videos. So let's pay careful attention to this. So let V be a vector space, and suppose we have a bunch of vectors v1, v2, vn. So the linear combination of v1, v2, vn with coefficients a1, a2, an, so these are real numbers, is the vector summation ai vi. What does this mean? This means you take vi, you take the ith vector vi, you do scalar multiplication of ai and vi, and that's a new vector. So accordingly we have n new vectors a1 v1, a2 v2, a3 v3, an vn, and then you add them up. And remember, since our axioms tell us that it doesn't matter which two we add first, what is called associativity of addition, you can just write it as a1 v1 plus a2 v2 plus a3 v3 up to an vn. Yeah, I don't need to specify which one I do first. So that's what we write as summation ai vi. Okay, so this is a new vector, and this new vector summation ai vi is called the linear combination of v1 v2 vn with coefficients a1 a2 an. Okay, so a vector v is a linear combination of v1 v2 vn if there are some scalars a1 a2 an, so that v is expressed as summation ai vi. Okay, so let's do a couple of examples. So we are going to look at the geometry first, and then we are going to look at the algebra. Okay, so the example here is 2 times 1 comma 2 plus 2 comma 1 is 4 comma 5. Okay, so what is 1 comma 2? So 1 comma 2 is over here. What is 2 comma 1? 2 comma 1 is over here, and then you take 2 times 1 comma 2, you scale 1 comma 2 by 2. So the new vector you get after scaling is this thing here, which is 2 comma 4. So you have 2 comma 4 plus 2 comma 1, use the parallelogram law and you get 4 comma 5. So of course you can do this algebraically, but that's not the point. The point we want to make here is that we have expressed 4 comma 5 as a linear combination of 1 comma 2 and 2 comma 1. And what is the linear combination? It's with the scalars 2 and 1. So 2 times 1 comma 2 plus 1 times 2 comma 1. So if there is a 1 times something, we suppress it. So 2 times 1 comma 2 plus 2 comma 1 is 4 comma 5, and the working out is clear. Okay, and we can say more, right? Each of the vectors in the expression is a linear combination of the other two vectors, right? So what are the three vectors we are talking about? We are talking about 1 comma 2, 2 comma 1 and 4 comma 5. We have expressed 4 comma 5 as a linear combination of 2 comma 1 and 1 comma 2. So instead we could express 1 comma 2 as a linear combination of 4 comma 5 and 2 comma 1. This is clear, right? Because you can take 2 comma 1 on the other side and you can divide by half. That's what we have got here. So the coefficients here are half and minus half. And similarly you can express 2 comma 1 as a linear combination of 4 comma 5 and 1 comma 2. So that is to do that you take 1 comma 2 on the other side and then you exactly get the second expression written here. Okay, so we can do other things. So this is all some manipulation of expressions, but this manipulation is important because it is going to lead us to a definition. Okay, so you can rewrite this expression as 2 times 1 comma 2 plus 1 plus 2 comma 1 minus 4 comma 5 is 0 comma 0. So we have taken that first expression on the top and moved 4 comma 5 to the left, yeah, by subtracting it out. And so what we get is on the right hand side, we get the vector 0. So we have a linear combination of these three vectors by some scalars, yeah, and these are non-zero scalars, yeah. So the coefficients here are non-zero. What are the coefficients? 2, 1 and minus 1. And with these coefficients, 0 is a linear combination of these three vectors 1 comma 2, 2 comma 1 and 4 comma 5. Okay, so I'll ask you to remember that picture in the previous slide along with this observation. Let's do one more. Okay, so here we have 3 times 2 comma 1 plus 2 times minus 2 comma 3 is 2 comma 9. So what is 2 comma 1? Here's 2 comma 1. And what is minus 2 comma 3? Here's minus 2 comma 3. So if we scale these, so 3 times 2 comma 1 is exactly this large thing we get here, which is 6 comma 3, and 2 times minus 2 comma 3 is this larger vector we get here, which is minus 4 comma 6. And then when we add them, we use the parallelogram law and we get the vector 2 comma 9. Okay, so what have we done? We have expressed 2 comma 9 as a linear combination of the vectors 2 comma 1 and minus 2 comma 3. Yeah, the algebra is what we just did and the expression is written here. So now again we can take these three vectors 2 comma 1, minus 2 comma 3 and 2 comma 9, and we can write any one of these as a linear combination of the other two. So already we have written 2 comma 9 as a linear combination of the first two. Now here's how we write 2 comma 1 as a linear combination of minus 2 comma 3 and 2 comma 9. Namely, we can take minus 2 comma 3 on the other side and then we can divide by 3, and that's the expression we get here. Or we could write minus 2 comma 3 as a linear combination of 2 comma 9 and 2 comma 1. How do we do that? We take 2 comma 1 on the other side and then we divide by half, and indeed that's the expression we get. Okay, so this is similar to what happened before, and once again instead of writing it this way, there is a third way we can write this expression, namely by taking 2 comma 9 on the other side and that gives us 0, the 0 vector on the right. So that's 3 times 2 comma 1 plus 2 times minus 2 comma 3 minus 2 comma 9 is 0 comma 0. So again, what do we observe? The 0 vector is a linear combination of 2 comma 1 minus 2 comma 3 and 2 comma 9 with non-zero coefficients. So this is the important part. What are the coefficients here? The coefficients are 3, 2 and minus 1. Okay. So I should point out, I am emphasizing this non-zero coefficients. What happens if your coefficients are 0? If you take a linear combination of any vectors v1, v2, vn with 0 coefficients, that is always going to give you 0, right? Because the linear combination will be 0 times v1 plus 0 times v2 plus 0 times vn, which of course is the 0 vector. Okay. So the point is, here you can do it with non-zero coefficients. Okay. So you can always do it with 0 coefficients, but it's not clear you can do it with non-zero coefficients, and if you can, then there's something special happening, right? So remember, all these 3 vectors were on the same plane. Yeah, this is the key point. Okay, let's do an example in R3. So in R3, let's take these 3 2 vectors. So we have 2 comma 2 comma 0. So this is the vector 2 comma 2 comma 0 out here. Yeah, so this plane has been drawn, I mean this xyz axis has been drawn a bit differently than we usually draw it for the purpose of illustration. So this is the xy plane. So on this we have the vector 2 comma 2 comma 0. On the left side, this is the yz plane. On this we have the vector 0 comma 2 comma 1, and then we scale these. So if you scale this, you get the vector 0 comma 4 comma 2. Here we get the vector 3 comma 3 comma 0, and you use the parallelogram and you add them, and what you get is 3 comma 7 comma 2. So you can check that this is the, by projecting down to the xz plane, what we get, and by projecting to the y-axis and so on. Yeah, that's what these other dashed lines are indicating. Okay, so what does this mean in terms of linear combinations? So in terms of linear combinations, what we have seen is in R3, the vector 3, 7, 2 is a linear combination of the vector 0, 2, 1 and 2, 2, 0. Okay, and the coefficients were 2 and 3 halves. So that's the expression, we just did that. So we can again play the same game. So instead of writing 3, 7, 2 as a linear combination of these two, we could instead write, let's say 0, 2, 1 as a linear combination of the other two, 3, 7, 2 and 2, 2, 0. Yeah, how do we do this? Move the other term on to the right side and then divide by the corresponding coefficient. Okay, or you could write 2, 2, 0 as a linear combination of 3, 7, 2 and 0, 2, 1. Again same idea. So I'll suggest you check this. Okay, and then again I can do the same thing that I have done before, namely I can move the 372 in the original expression to the left hand side and get 0, 0, 0 on the right hand side. So what is the net result? That the 0 vector is a linear combination of 0, 2, 1, 2, 2, 0 and 3, 7, 2 with non-zero coefficients. Okay, and again I'll encourage you to check that these 3 vectors lie on the same plane. So we can in fact get the equation of that plane. So the equation of the plane containing the 2 vectors 0, 2, 1 and 2, 2, 0 is 2x minus 2y plus 4z is 0, and you can check that the third equation, the third point, indeed lies on this plane. Okay, so these 3 lie on the same plane. Okay, and that is, so the geometry is somehow converting to this observation that if you take these 3 vectors, you can write 0 as a linear combination in a non-trivial way, meaning with non-zero coefficients. Okay, so suppose we choose now a point or a vector which is not on the plane. say 1 2 0. So 1 2 0 is not on the plane. How do I check 1 2 0 is not on the plane? I plug in these values into the equation of the plane and get that it is not 0. Okay, so 2 times 1 minus 2 times 2 plus 4 times 0 is not equal to 0. Okay, so that's why it's not on the plane. So we claim then that 1 2 0 cannot be written as a linear combination of 0 to 1 and 2 to 0. Yeah, so we saw earlier that in the earlier example that the third vector indeed was on the plane. So maybe we can go back and check what that was. So it was 372, and 372 does satisfy this equation. Yeah, because 2 times 3 is 6 plus 4 times 2 is 8. So 6 plus 8 is 14 minus 2 times 7 is 0. Okay. So let's look at 1 2 0. We saw already it doesn't satisfy that equation, so it's not on the plane. And now the claim is it cannot be written as a linear combination of 0 to 1 and 2 to 0. So let's do this by contradiction. Suppose you can write this as a linear combination. So you have a times 0 to 1 plus b times 0 2 to 0 is 1 to 0. So a and b are the coefficients. Then we can work out what are the expressions in each coordinate. So the expressions in the first coordinate is just 2b. The expression in the second coordinate is 2 times a plus 2 times b, and the expression in the third coordinate is just a, and we equate it to the right hand side. So if we do that, then we get 2b is 1, 2a plus 2b is 2, and a is 0. That means b is half and a is 0. That's what we get from the first and third equations. And if that happens, then 2a plus 2b cannot be 2. So that means there is no a and b which satisfies this equation, right? So our assumption that there is an a and b is wrong. So there is no such a and b. Okay, so what does that imply? That implies that this vector 1 2 0 cannot be written as a linear combination of 0 to 1 and 2 to 0. Okay, and we can equally well conclude from here, and I will suggest that you check this, that if you do a times 0 to 1 plus b times 2 to 0 plus c times 1 to 0 is equal to 0 0 0. Suppose I ask, can I get a, b and c such that it is 0 0 0. So what the above discussion tells us is that the only possible choices for a, b, c are 0 0 and 0, meaning all three of a, b and c must be 0. Yeah, so what does this mean? So this is now the the negation of the observation we did earlier. So the only way the 0 vector is a linear combination of these three vectors is if the coefficients are 0. Yeah, so in the previous examples where those vectors were on the same plane, we could write 0 as a linear combination of those three vectors with non-zero coefficients. But here there is no way of doing that. The only way of writing 0 is if your coefficients are 0. Okay, and that is the trivial way, right? Because if the coefficients are 0, we get the 0 vector. Okay, so now we can define linear dependence. Okay, keep this geometric picture in mind and keep the algebraic expressions in mind. A set of vectors v1, v2, vn from a vector space V is said to be linearly dependent if there exist scalars a1, a2, an, not all 0, such that a1 times v1 plus a2 times v2 plus an times vn is 0. Okay. So the key point here is that these a1, a2, n are not all 0. Okay. So there is a way of writing 0 as a linear combination where the coefficients are not 0. At least some of them are not 0. Okay. So the equivalent way of saying this is that the 0 vector is a linear combination of v1, v2, vn with non-zero coefficients. Okay, meaning when I say with non-zero coefficients, that means some of the coefficients are not 0. It's not, we don't need to say that all coefficients are non-zero. Okay, some non-zero coefficients. Okay, fine. So just to jog our memory, the first three examples we did, the two examples in R2 and the third one in R3, the three vectors we had were linearly dependent. That is what we saw. Yeah, because we could write as 0 as a linear combination of these 3 vectors where the coefficients were non-zero, meaning not all of them were 0. The fourth example, meaning where we had the vector 1, 2, 0, that example the 3 vectors in question are not linearly dependent. Okay, so next video we will see that they are what are called linearly independent. Okay, so consider the vectors 2, 3, 7 and 5 thirds, 5 halves and 35 by 6 in R3. So you can check that if you multiply this second vector by 6 and you multiply the first vector by 5, then you get the same vector. So in other words, if you do 5 times 2 comma 3 comma 7 minus 6 times 5 thirds comma 5 halves comma 35 by 6, that is 0, 0, 0, 0. So at least one of these coefficients is non-zero. In fact, in this case both of them are non-zero, and so these two vectors are linearly dependent. Okay, these two vectors 2, 3, 7 and 5 thirds, 5 halves, 35 by 6 are linearly dependent. And note that the way this worked is that they are scalars, they are scalar multiples of one another, right. If you draw 5 thirds, 5 halves, 35 by 6, and if you draw 2 comma 3 comma 7, they will appear on the same line. That is clear, because if you scale one of them by 6 and the other by 5, they give you the same vector. Okay. So in other words, when you have two vectors, what we are saying is if two vectors are linearly dependent, then essentially one is a multiple of the other. Okay, so let us continue and study one more example. So consider the following 3 vectors in R3: 2, 1, 2, 3, 0, 1 and 10, minus 4, minus 2. So here is an equation that we can check easily: 2 times 2, 1, 2 minus 3 times 3, 0, 1 plus half times 10 minus 4 minus 2 is the 0 vector. So from here it follows that these 3 vectors are linearly dependent. Let us do this checking just to be sure. So the checking here is 4 comma 2 comma 4 minus 9 comma 0 comma 3 plus 5 comma minus 2 comma minus 1. Well, the first component is 4 minus 9 plus 5, that is indeed 0. The second component is 2 minus 0 minus 2, which is 0, and then the third component is 4 minus 3 minus 1, which is indeed 0. So this is indeed this equation is indeed correct, and this tells us that there is a linear equation satisfied by these 3 vectors with non-zero coefficients, which equates to 0. So they are linearly dependent. Let us continue and append a vector to this set. So this set is now 2, 1, 2, 3, 0, 1, 10, minus 4, minus 2 and 2, 3, 7. So we have appended one more vector to this set, and we can ask, is this set now linearly dependent? Is this a set of linearly dependent vectors? And the answer is, well, certainly it is, because since the original set, meaning the set with 3 of them, was linearly dependent, we can write down the same equation, but we also have to include the new vector 2, 3, 7. So what do? We put the 0 coefficient for that, and we of course still get 0, 0, 0. So you can, if you are not convinced, you can do this checking by yourself, and from here it is clear that this set is linearly dependent. So what is the point? The point is this: we get the following fact. I mean, this is by observation, but you can clearly see, because the proof is the same. If a set is linearly, if a set of vectors is linearly dependent, then so is every superset of that set. Yeah. So if V1, V2, Vn is linearly dependent, then V1, V2, Vn, and you add one more vector W, then V1, V2, Vn comma W is also linearly dependent. Yeah. You can add as many vectors as you want; those are all linearly dependent. Okay, so I guess that finishes what the material in this video. Let's quickly recall that we have seen in this video that when a set of vectors in a vector space is linearly dependent, and importantly in the case of R2 or R3, what this means is that if you have two vectors are linearly dependent, they must be on the same line. If you have three vectors are linearly dependent, they must be on the same plane. This is the geometry of what's going on. Okay. And finally, to check these things, we have to solve some equations. So finally, this kind of checking is also related to solving systems of linear equations. Okay, so thank you.